Learning outcome 3. Be able to manipulate trigonometric expressions and apply trigonometric techniques. This is not going to be right angle triangles and that stuff. We've done all that in Unit 4. This is something a bit different. So P7, 2 P's and a distinction in this assignment. Sketch a graph of a sinusoidal trigonometric function and use it to explain and describe amplitude, periodic time and frequency, which you will probably have done in a slightly different form in electrical principles last year anyway. Okay. Second, P8, use 2 of the compound angle formulae and verify their relationship. That you probably won't have done before. I don't fully understand what's in Unit 4. I don't think that is. You will have done some trigonometry, but not that. And then D1 is use a graphical technique to determine the single wave resultant from the combination of 2 waves of the same frequency, and verify the result using trigonometric formulae. That's the distinction question, where you're expected to have a lot less hand-holding from me, expected to use what you learn in the sessions to do that question. Now, I've had a good look through the spec, and with this particular topic, and to a certain extent the next one, and this middle task here is the tricky one. It says I should give you all a different trigonometric identity to prove. Pretty hard for me to find 23 or 22 different ones. That's impossible for me to do. Or I should do it as an in-class test, i.e. quiet, not talking to each other. But that's not an exam, books open, I'm here for a little bit of guidance, but you're not helping each other. So that's how we're going to do this assignment over a period of a couple of weeks, see how we go. So I'm going to teach you, give you a look at the assignment, we'll talk through the assignment, and then sit down, we'll spread out a bit more, and you'll work on it on your own. Okay? Yeah. So that's how this one's going to be done, and probably the next one will as well. And look, if I look back at the spec, some of the other stuff we've done should have been done that way as well. We could actually be picked up that by the external, that we're not either giving you individual tasks to do with different numbers or doing it as an in-class test. All right? Sorry? Yeah, but you all kind of sat there and helped each other. Yeah. I'm not stupid. Right. I won't. Right. Anyway, moving on from that. Drill. Without a calculator, what's the sine of 0 degrees equal to? Well done. Sine of 0 is 0. What's the sine of 90 degrees equal to? 1. Sine of 180 degrees? 0. Well done. Cosine of 0 degrees? 1. Cosine of 90? 0. Cosine of 180? Minus 1. Well done. Right, guys. 360 degrees in radians. Anyone remember radians? How many radians equal 1 revolution of a circle? 2. 2. Close. Not that close. 2 pi radians in a full circle. Okay. If you're going to study engineering to any level from here and beyond, you'll need to be able to deal with angles in both degrees and radians, and know when to switch your calculator between degrees and radians as well. Okay? 2 pi over 2 radians to an angle in degrees. What is pi over 2 radians in degrees? Who said that? What was that? I heard something. 90 degrees, yeah. The next page has a graph with 0 to 360 on an x-axis. Use it to sketch functions sine x and cosine x. Right guys, listen, sine wave, sine x I'm going to do in red. We've already looked at the points. Sine of x at 90 is 1, is 0 there, is 0 there, is minus 1 at 270 and there. So you should have a function that looks something like that. Yeah, I've drawn several hundred of them. Okay, and then cosine of x is equal to 1 there, 0 there, minus 1 there, 0 there, and 1 there. So something like that. Okay, not quite so good. And something we'll come back to perhaps at some point is there's 90 degrees of phase difference between cosine and sine. Alright? Or there's pi over 2 radians between sine and cosine functions. Converting between angles. Guys at the back, can you stop talking please? So, converting between angles in degrees and angles in radians. There's 2 pi radians in a full circle. Okay, so we got an angle in degrees and we want it in radians. We take that angle in degrees and multiply it by 2 pi over 360. You might have also seen it as pi over 180, you're doing the same thing. That's a full circle. That's the part of the full circle. And that's a full circle in terms of radians. Okay. We do, so for example, 30 degrees, we do 30 times 2 pi over 360. 1/6 pi, 0.524 if we evaluate pi. And I'm going to say to you now, if you don't have to, don't evaluate pi. Leave it as pi. Particularly if you're going to use that value in another formula to do another calculation, you're far better off leaving it as 6th pi in that calculation, and you keep all the accuracy. As soon as you evaluate pi, remember what it is, it's a never-ending decimal, and you're going to round it off, and you're going to create some inaccuracy, and you're also going to create numbers with a lot of decimal places that you could write down wrong. Yep. Okay? So get used to leaving pi as it is. And quite often, and you're going to see an example a bit later on, where you do a calculation, and the two pi's are one divided by the other, and they disappear anyway. They eliminate themselves eventually. Okay? The other thing is, this is the angle in terms of degrees. So if we've got an angle in radians, we multiply it by 360 over 2 pi. An example, 0.75 radians is 42.97 degrees to 4 significant figures. Okay? On your calculators, if you don't already know, to shift between degrees and radian measurements, you press the shift button, you press the mode setup button, and then you pick the number 3 or the number 4 to switch it between degrees and radians. And usually when I can't get the answer you got, Mike, that's because the guy or lady is working with their calculator in the wrong mode. Okay, expressing angles in radians as a multiple of pi. As I've already said, it's quite common and useful to keep angles in radians in terms of pi. So I've made a little table there with angles at every 45 degrees and what they are in radians in terms of pi. So if 0 degrees is 0 radians, 360 is 2 pi, 180 must be pi radians, half of that must be pi over 2, and halfway between them, 45 degrees, must be pi over 4, 3 pi over 4 for halfway between those two, and the same on this side. And those fractional multiples of pi are the easiest way to deal with those angles in radians in most cases. And then evaluate, if you need a number in actual radians, evaluate it right at the end. Alright, so we're going to be using angles like that, and I may well give you angles. If I give you an angle pi over 3 pi over 4 radians, you know it in radians because I've included pi. You wouldn't have 3 pi over 4 degrees. Alright? So, moving on yet again, if we look at this function, y is equal to sine theta in a bit more detail. So, angles in degrees here again at the moment. We can produce a graph as shown with theta being the angle in degrees. More general form for the sine wave function with the angle in degrees is y is equal to a times the sine of theta. What's the constant a? Amplitude. Yep. This distance up that arrow there is a, the amplitude. What have I put an arrow across there for, do you think? If this was time, that would be something, yeah, but what would we say? That's one cycle. Okay? Yeah, if with your angles in degrees, you go through one cycle in 360 degrees, if that's just a plain sine on that angle. Okay? We're going to look at something else in a minute. Alright? Everybody happy with that and understand that? Yeah? So, using the form y is equal to a sine theta, and that graph is included on the axis below, with a is equal to 1, sketch the graph of the following functions. Y is equal to 2 sine theta, and y is equal to half sine theta. Right guys, what we should have for the y is equal to 2 sine x, I'm going to do in blue. It's going to peak there, it's going to cross through 0, it's going to peak at -2 and come back to there. So you should have, and that's what most of you have got, that kind of thing. For y is equal to 2 sine x, and for y is equal to half sine x, it's only going to reach a half at each peak. So you should have something along those lines. Yep. So that's what changing the amplitude does to a sine function with the angle in degrees. Okay? Frequency of a waveform in hertz. Alright? The frequency f, hertz, of a waveform is the number of cycles that take place in a time of 1 second. They used to call it cycles per second, and the Americans still talk about 50 cycles. But the SI unit of frequency is hertz. Yeah. AC mains in this country, 60 hertz, 50 hertz. AC mains in the United States and Japan, to name two, is 60 hertz. All right. So we can add this to the sine function in the following way, where f is the frequency. Guys, keep talking up the back there. We can change the function to y is equal to a sine of f times the angle. So if we look at the plot that I've given you, and I know yours is in black and white, but on here we got the red function, that is y is equal to sine theta, i.e. f is 1. Blue waveform is y is equal to 3 times sine theta. The frequency is 3. It's going to do 3 times as many cycles in the same time as the first one did 1. So here's 1 cycle for the red one there. And in the same 360-degree angle notation, the blue one is doing 1, 2, 3 cycles, 3 hertz compared to the other one. All right. So the blue waveform repeats 3 times in the same time that there is 1 cycle of the red waveform. So we're gradually building. On that graph, I'd like you, it shows y is equal to sine x, i.e. f is equal to 1. Sketch the graphs, y is equal to 2 times the sine of 2 theta, and the graph of half sine half theta. From the angular frequency, f can be found using f is equal to omega over 2 pi. So we can use that relationship to get the frequency out in hertz if we want to. So the standard form for a sine wave in this format is y is equal to I, the amplitude, times the sine of omega, the angular frequency, multiplied by t, the time in seconds. It's normal for omega to be expressed in a multiple of pi, as in the examples on the following page. So you don't normally express omega as a number on its own, because it would have a never-ending decimal attached to it. Because you're multiplying it by pi, you would express it as a multiple of pi. So, on that, from the function, if y is equal to 2 times the sine of 4 pi t, what's the frequency in hertz? So if omega is equal to 4 pi rads per second, f is equal to 4 pi over 2 pi equals 2 hertz. There's your example of pi cancelling itself out. On that diagram, the red waveform is y is equal to 2 times the sine of 2 pi t. Frequency is 1. The green waveform is y is equal to 2 times 4 pi t. Double the frequency. So the red one, doing 1 waveform from there to there. The green one, in the same amount of time, is doing 2 complete cycles. So we doubled the frequency from 2 pi to 4 pi. Omega's changed from 2 pi to 4 pi. Get twice as many cycles per second. All right? I've gone backwards. Go forwards. The period. Okay? Period of a sine wave. Graph below is a graph of the function y is equal to 2 sine 4 pi t. The frequency is 2 hertz. Yep. We'll get used to that eventually. If that's 4 pi t, divide it by 2, that must be 2 hertz. 10 pi t, 5 hertz. 100 pi t, 50 hertz. Okay. The period is the time taken in seconds for one cycle. So now we've got our x-axis being t in seconds. We have a period for one waveform in seconds. This is frequency of 2 hertz. It's going to do 2 cycles in 1 second. Therefore, one cycle here is taken 0.5 seconds. We can always find the period of a sine wave from the period t is equal to 1 over f. Consequently, we can find f as being 1 over t. They are reciprocals of each other. So if we know the period, we can find the frequency. If we know the frequency, we can find the period. Determine the frequency of the following in hertz and the period of the waveform in seconds. Okay, there's some problems for you to have a go at. Determine the angular frequency omega of the following as a multiple of pi. And for each of the following functions, determine the amplitude, the frequency in hertz, and the period of the waveform in seconds. While you guys are having